Section 3 is general container types and behavior, and the objective is recognize general container shapes and their associated behaviors. Chapter 2 introduced container shapes and provided basic information regarding basic container types and contents for awareness level personnel. The following sections will provide additional container recognition information based upon transportation mode or fixed facility with a brief description of common stressors leading to breaches and releases. Some basic generalization may be made about a hazmat incident based on the type or types of container or containers involved. For example, if the incident involves a pressure container, any product released is likely to be a gases or a liquid that rapidly evaporates and expands into a gas or vapor. Once released, the hazard materials will behave like a gas depending on its properties and the environmental conditions at the scene. Table 5.1 provides a basic overview of the four major types of containers and their relationships to aspects of the general behavior model. Skill Sheet 5.1 provides steps to analyze a hazard materials incident to identify potential hazards. As a precaution, remember to approach each hazmat incident as a unique situation regardless of commonalities between incidents. In addition to the general container shapes, first responders should be familiar with the basic concepts of pressure and their measurements. You have pounds per square inch, which is PSI, which is the common measurement for pressure in the English or customary system. Then atmospheric pressure is the force exerted by the weight of the atmosphere at the surface of the earth. Atmospheric pressure is greatest at low altitudes constantly. Its pressure at sea level is used as a standard. At sea level, the atmosphere exerts a pressure of 14.7 psi. A common method of measuring atmospheric pressure is to compare the weight of the atmosphere with the height of a column of mercury. The greater the atmospheric pressure, the taller the column of mercury. And then pressure at gauge is described as a unit of pressure relative to the surrounding atmosphere. The customary system unit is pounds per square inch gauge, or PSIG. For example, at sea level, a reading of 30 pounds per square inch on a tire gauge represents an absolute pressure of 44.7 psi because the gauge was calibrated to zero at atmospheric pressure of approximately 14.7. We are going to talk about pressure containers now. They are carrying gases or liquids. In general, all pressure containers are constructed to prevent accidental releases. Pressure containers are subject to stress when holding materials, and heating or cooling may increase or reduce the stress. If pressure containers are damaged or subjected to additional stress, they may fail catastrophically and/or BLEVE. Hazmat incidents involving pressure containers are dangerous to emergency responders and the public. First responders at hazmat incidents involving pressure containers need to consider the following common stressors. Thermal exposure to heat or flame can cause pressure containers to BLEVE. Chemicals released, like corrosive gases, can cause additional damage to the container. Pressure on the container can increase by reactions of the contents. With mechanical, accidents may cause mechanical stress, particularly to the container fittings, and severe accidents may cause damage to the container walls. Pressure containers can experience any type of breach, although releases from pressure relief devices and/or damaged fittings are most common. Runaway cracking is associated with BLEVEs. Punctures, splits, and tears are rare, although violent accidents such as railway derailments or highway accidents may involve enough force to damage welded seams or cause punctures through pressure container walls. Pressure containers release rapidly expanding gases or liquids that quickly evaporate and expand into gases or vapors. Releases can occur through pressure relief devices, rapid relief, or as leaks through damaged attachments and fittings. Common dispersion patterns from pressure containers include hemispheric pattern that would happen from a levee, a cloud pattern, which would be above the container if there is little wind and the release is intermittent or short in duration. A plume pattern will depend on the vapor density, terrain, particularly if the vapor density is greater than 1, and wind speed. A cone-shaped pattern happens when a steady release of product from a pressure container releases and expands from the point of release outward. The cone will be directed downwind in accordance with the prevailing wind direction. A warning is to use extreme caution when handling pressure containers that have been involved in an accident. Cryogenic containers, like pressure containers, are solidly constructed to prevent accidental releases. Cryogenic containers are durable containers that insulate their contents, keeping them cold. They maintain cold temperatures through the use of insulating materials and a vacuum space between the two container walls. Insulation between the exterior and the interior wall of the container keeps the product cool but does not provide protection against breaches. The container's external support structure is not designed to handle the temperatures inside the container. Common stressors to consider at hazmat incidents involving cryogenic containers include: the first is thermal. If a breach occurs, the extreme cold of the released product may cause damage to the container or fittings. When exposed to heat or flame, cryogenic containers can levy. Although this is unusual, if vacuum is lost, the product will heat rapidly and may blow the rupture disc or the relief valve. If the system cannot relieve pressure quickly enough, the container may rupture. Damage to the outer jacket and insulation may result in loss of vacuum. With chemical, normal stressors are due to exposures from the outside contact on the container. An incorrect chemical added to a cryogenic tank may cause corrosion. And with mechanical, accidents may cause mechanical stress, particularly to the container fittings. Severe accidents may cause damage to container walls, creating loss of vacuum within the vacuum space of the container. A note to remember is that venting is a function of some cryogenic containers and may not indicate a system failure. Cryogenic containers can experience any type of breach, although release from pressure relief devices and/or damaged fittings are most common. Punctures, splits, and tears are rare, although violent accidents such as railway derailments or highway accidents may involve enough force to damage both exterior and interior container walls. As a precaution, cold stress and heat stress can result in similar failures. Cryogenic containers are designed to handle extremely cold temperatures. However, the external support structure of the container is not designed to do so. If cryogenic materials leak, the support structures can fail without warning due to stress failures. If other containers are involved in a wreck or derailment with cryogenic containers, leaks from the cryogenic containers may cause failure to other containers due to cold stress. Cryogenic containers release cold liquids or vapors that rapidly boil into expanding gases. Common releases include through pressure relief devices, rapid relief, or as leaks through damaged attachments and fittings. Typical dispersion patterns from cryogenic containers include hemispheric, cloud, plume, and pool. With liquid holding containers, they come in a variety of designs and construction types depending on the size, mode of transportation, material contained, use of, and other factors. Liquid holding containers may have the following characteristics. They are extremely durable, such as a tank car. They can be fragile, such as the glass bottle. They may fail when subjected to fires, and they are less likely to fragment as they levy. They will transport materials that plumerize, and if uncontrolled, plumerization or chemical stress happens, it may create enough stress to cause container failure, and could be explosive in nature. While streams and pools are common dispersion patterns for liquids, many liquids also release vapors that act like gases. All dispersion patterns can be associated with liquids depending on the product and container. And finally, with solids holding containers, they also come in a variety of design and construction, types depending on size, mode of transport, material contained, use, and other factors. Many containers used for liquids, such as drums, are also used for solids, but some solid hazard materials have unique containers. Most solid holding containers will be damaged via mechanical stresses rather than the physical properties of the materials contained in them. Exceptions include reactive materials such as oxidizers, peroxides, explosives, and water-reactive materials. Common breaches of solids holding containers include punctures, splits, and tears. Pneumatic loading and unloading attachments may be damaged in accidents. Common releases result in the following spills and leaks. Detonation, which occurs when oxidizers, peroxide, explosives, and water-reactive materials are involved. Violent ruptures will happen when reactive solids are released. Clouds, cones, or via irregular dispersions may happen when solids are dispersed, and explosions such as detonated explosives disperse in a hemispherical dispersion. The review question of this section is, what are the major types of containers that hold hazardous materials? Look on pages 226 through 233 of the manual for your answers.